The definite integral. Our objectives in this lesson are to form Riemann sums, define a definite integral as the limit of Riemann sums, approximate a definite integral using Riemann sums, know conditions that guarantee a definite integral exists, find a definite integral using the limit of Riemann sums and graphically, and use properties of definite integrals. Let's begin by discussing what is a Riemann sum. When we think of a Riemann sum, we should think of the sum of areas of rectangles. I like to think R for Riemann, R for rectangles. Riemann is the last name of a German mathematician who did his studies in this area, so we call it after him. We often use Riemann sums to approximate the area of the region enclosed by the graph of f, the x-axis, and the lines x equals a and x equals b. A left Riemann sum means that we're using left endpoints for each subinterval, while a midpoint Riemann sum is formed using the midpoint of each subinterval, and the right Riemann sum is formed by using the right endpoint of each subinterval. We explored different uses of endpoints last time when we talked about area, where we took the sum of the area of each rectangle, the function value being the height of the rectangle, and delta x being the width of the rectangle. Let's explore the connection between Riemann sums and definite integrals. Let's start by talking about the parts of a definite integral. The integral sign is S-shaped to remind us that it comes from a sum, like S for sum, but we call this the integral sign. The limits a and b of the integral represent the lower bound. This is called the lower limit of integration. And b is called the upper limit of integration. These coming from our interval starting at a and ending at b. The function in the integral expression is called the integrand. And you might recognize dx from when we did differentials. This is the differential of the variable of integration. So why these parts for the definite integral? The definite integral, if we look down here, is defined as the limit as n approaches infinity of the sum from I equals 1 to n of f of c sub I times delta x. We might remember from our work last time that this right here represents an area. However, a definite integral actually represents the net area, meaning the area above the x-axis minus the area below the x-axis. Let's take a moment to explore why that is. We're going to look at this function, f of x equals x squared minus 2, specifically over the interval 0 to 2. So just from 0 to 2, looking at the area between the function and the x-axis. So in our first section, we have area that is completely below the x-axis, and in the second section up to 2, the area is completely above the x-axis. Now, if we look at the format of how we find that definite integral, which before we were calling the exact area between the function and the x-axis, we are multiplying the width of the rectangle times the height of the rectangle to get to the area of each rectangle. Now, if I just do one representative rectangle in this first section, I have a delta x that is a width of some amount. And let's say I use a right endpoint to go find a function value. And I go across, and there's my rectangle to estimate that area. Well, this function value right down here, which we're calling f of c sub 1, since that's our first function value, goes down to a negative function value. So our delta x is a positive amount, our function value is a negative amount, so when we do f of c sub I, or c sub 1 in this case, times delta x, we're getting a negative times a positive, which leads to a negative value. Similarly, if I look at this section and I say here's a width, delta x, and I go up to the function on the right side, this is my f of c sub 2. Again, I still have a positive width, my delta x is positive, and this time a positive function value. So this f of c sub 2 times delta x is a positive times a positive, which yields a positive value. Now, the definite integral represents the sum of the function value times delta x, whether the function value is negative or positive. So this value yields a negative, while this value yields a positive, and I have to add those together. Now, in fact, the exact areas of these regions are as follows. The area of this first region, I'll call it a sub 1, is 5/3. But because it's below the x-axis, this would represent a value of negative 5/3. The exact area of that second region, we'll call it a sub 2, is exactly 1/3. And because it's above the x-axis, my function value positive, it yields a positive 1/3. Now, because my definite integral requires me to add the function value times delta x, and the function value is negative, I would be adding negative 5/3 plus 1/3. So I'm not doing a total of the areas, but rather anything that is above the x-axis yields a positive value. Anything below the x-axis, because of the negative function value, yields a negative value. So in fact, I'm subtracting the area above the x-axis minus the area below the x-axis. So it's important that we take note that the definite integral is not a representation of the area of the region, it's the net area of the region. Not the area, but the net area, or the area above the x-axis minus the area below the x-axis. It's also important that we note that if a function is continuous, then we will be able to take the definite integral. Continuity implies integrability. Thanks for watching.